Inside the space station, these same forces are at play, but on a micro scale. Furthermore, other forces contribute to the microgravity environment. The gentle push from the station's life support systems, the vibrations from machinery, and even the movement of the astronauts themselves can create tiny accelerations that disrupt a perfect state of freefall. It's not a perfectly pristine, force-free environment. This microgravity environment, however, is precisely what makes the International Space Station such a unique and valuable laboratory. Scientists can conduct experiments that would be impossible on Earth, where the overwhelming force of gravity masks more subtle phenomena. They can study how fluids behave without convection, how fire burns in a sphere instead of a teardrop shape, and how crystals can grow to a level of perfection unattainable on the ground. It's a playground for physicists, chemists, and biologists, allowing us to peel back a layer of reality and see the universe in a new way. So, the next time you ponder the floating astronauts, remember the deep physics behind the spectacle. They are not in a place where gravity has ceased to exist. They are in a sophisticated, high-speed vehicle that is constantly falling around our planet. This state of microgravity, this elegant dance of falling and missing, is not a bug. It's a feature. It's the key that has unlocked a new frontier of scientific discovery, allowing us to probe the fundamental nature of matter and life itself, all while riding the relentless, inescapable, and beautifully predictable force of gravity. Ask a child to draw the sun, and they'll likely use a yellow crayon. We see a yellow orb, but the sun's true color, before reaching Earth, is white. Our star is fundamentally white. It emits light across the entire visible spectrum. From space, without atmospheric filters, the sun appears as a brilliant white sphere. Our atmosphere scatters light, painting our sky and tinting the sun's color. The yellow sun is a terrestrial illusion. Rayleigh scattering causes the sun's color shift. Sunlight collides with nitrogen and oxygen molecules. Shorter wavelengths, like blue and violet, scatter more. This makes the sky blue. The remaining light appears yellow. At sunrise and sunset, the effect intensifies. Oranges and reds dominate, painting the sky with fiery colors. The sun's color varies daily, a beautiful demonstration of physics. This principle isn't just a neat piece of trivia. It has real-world implications for how we study our star and the universe beyond. When astronomers on the ground use telescopes to observe the sun, they must constantly account for the distorting effects of the atmosphere. The same scattering that colors the sun also blurs fine details and makes precise measurements more challenging. This is why some of the most revolutionary solar observatories, like the Solar and Heliospheric Observatory, or SOHO, or the Parker Solar Probe, are placed in space, far beyond the atmospheric veil. From their vantage point in space, these telescopes can capture the sun in its true, unfiltered glory. They see it as the intensely white star it is, and they can analyze the full spectrum of its radiation without atmospheric interference. This allows scientists to study the intricate details of the sun's surface, like sunspots and solar flares, with incredible clarity. By studying the sun's complete white light output, they can better understand the nuclear fusion processes happening in its core and the complex magnetic fields that govern its activity that can have profound effects here on Earth. Furthermore, understanding that the sun is a white light star helps us classify other stars throughout the galaxy. When we look at a distant star and see that it is yellow, like Alpha Centauri A, we know that its surface temperature is very similar to our sun's. When we see a reddish star like Betelgeuse or a bluish-white one like Rigel, we can immediately infer crucial information about their temperature, age, and mass. The color of a star is one of its most fundamental vital signs, and knowing our own sun's true color provides a crucial baseline for this cosmic comparison.